Another video of CS360, and in this video we will cover NP completeness and NP hardness. Okay, NP completeness. So to define the notion of NP completeness and NP hardness, we start by reviewing mapping reductions. So remember, if A and B are languages, then we had mapping reduction from A to B. What was this? This meant that there is a function f, which goes from the alphabet of A, the strings on the alphabet of A to strings on the alphabet of B. So here we're assuming like A is in sigma star and B is in gamma star. Okay, such that f is computable. Okay, and then if x is an A, so if x is an A, then f of x is in B. Okay, and if x is not an A, f of x is not in B. Okay, so what f does is it converts inputs to the question whether the input is an A. So it converts inputs x that may or may not be in A into inputs f of x, which may or may not be in B, such that if x was in A, then f of x is in B, and if x was not in A, then f of x is not in B. So it converts the question of whether something is in A into the question of whether something is in B. Okay, now f is also computable. So if you had an algorithm for deciding B, then you could decide A simply by taking an input x, computing f of x, and then using your algorithm for B to decide whether f of x is in B, and that would tell you whether x is in A. Okay, and this is called a mapping reduction. It maps the problem of whether a string is an A into the problem of whether a string is in B. Okay, and we denote it with a less than to remind ourselves that it means that if we had an algorithm for B, we get an algorithm for A. So in other words, B is like harder than or equal to A in terms of decidability. Okay, and we had that if B is decidable, then A is decidable. If B is recognizable, then A is recognizable. All right. Okay, so now we're going to define polynomial time mapping reduction. So polynomial time mapping reduction we denote like this. Okay, so we denote this. This means that there is a mapping reduction. A mapping reduction f from A to B, such that f is computable in polynomial time. Okay, so that's what this means. Okay, so in other words, before we had a way of converting the question of whether a string is in A to the question of whether a string is in B, and that conversion was computable. Now that conversion is efficiently computable, where we take polynomial time to mean efficient computation. Okay, so it's the same thing as before, except the conversion is now efficient. Okay, so now if you had an efficient algorithm for B, you could convert that into an efficient algorithm for A, where you take an input x that may or may not be an A, you compute f of x using your efficient algorithm for computing f, and then you use your efficient algorithm for B to decide whether f of x is in B, and that gives you an efficient algorithm for whether x is in A, where we use polynomial time to mean efficient. Okay, so polynomial time algorithm together with another polynomial time algorithm is just going to give you another polynomial time algorithm. Okay, so combining these algorithms remains within this efficient range. Okay. Okay, so this is the notion of polynomial time reduction. Okay, and so note that if if B is in NP, If we have a mapping reduction from A to B, then A is an NP. Okay, and this is not too hard to show. You know, it's sort of it's the same idea that you can convert the problem of whether X is an A into the problem of whether X is in B, right? So I mean, you can do this with non-deterministic Turing machines or with verifiers. So for example, if B is an NP, then we have a verifier V for B, right? We have a verifier B V for B, and we can define a verifier like V prime for A, such that V prime of XW runs V of f of X W. Okay, so the verifier V prime expects a proof of W that f of X is in B, right? So V prime expects a proof that f of X, not X, but f of X is in B. And if it receives such a valid proof, then it will agree that X is an A. Okay, now V prime can compute f efficiently because it's polynomial time. So V prime can convert this pair XW to the pair f of XW, that it can do. And then it can run V because that's polynomial time. Okay, and note that f of X itself is polynomial sized in X because f only took polynomial time to compute. So in polynomial time, you can only output polynomially many bits. So f of X is polynomially sized in terms of X, the string f of X. And then this W must be polynomial sized in f of X, or there must exist a witness that's polynomial sized in f of X. And polynomial sized in f of X is also polynomial sized in X because the composition of two polynomials is polynomial. So there must exist, so if X is an A, in other words, there must exist some string W that causes V prime to accept, and the string W will be polynomial sized. And you can verify from here that all the other conditions hold. So for example, if X is not an A, there will not be any witness that causes V prime to accept. Okay, so this is a valid verifier for A, given a valid verifier for B, a polynomial time verifier. Okay, so so this less than or equal to plays nicely with NP, such that if B is in NP, then A is also in NP. And same thing, if B is in P, then A is in P. If B is in P space, A is in P space. If B is in X, A is in X. If B is in NEXP, A is in NEXP, and so on. Okay, so it's a very convenient thing for relating the difficulty of problems to each other. If you have a reduction between two languages, then the difficulty of one really is kind of like greater than or equal to the difficulty of the other in terms of any of these classes like P and NP and P space. Okay, so now we can define, we say that a language A is like hard for a class. For a class C. So this is like a script C. If this holds, if there's a polynomial time reduction from B to A for every language in the class. So for example, A is NP hard if for all B in NP, and this is an if and only if, it's a definition. If for all B in NP, there's a polynomial time mapping reduction from B to A. Okay, so that makes A harder than or equal to every single language in NP. That's the definition of being NP hard. Okay, now as we defined it, it doesn't even necessarily have to be true that there exist NP hard languages, right? So we don't even know so far that there exist NP hard languages. But still, this is like a valid mathematical definition. So a language is NP hard if it satisfies this. And similarly, a language is hard for any other class C, like P-space, for example, if it satisfies that for all languages in the same class C, so in P-space. So P-space hard means that A is harder than everything in P-space or equal to. And by hard or equal to, I mean mapping reduction. Okay, polynomial time mapping reduction. Yeah. So this is the definition of hardness, and specifically NP hardness is one of the most useful notion of hardness. Okay, and let's also define completeness. So we say that A is complete for a class C. So remember, the script C here is always it's a set of languages, a class of languages, whereas A is just a language. Okay, so A is one language, and C here is a set of languages, a class of languages. So we say A is complete for a class C if A is in the class C and A is hard for C. Okay, so so in other words, in other words, A is NP complete if A in NP and A is NP hard. Okay, which remember that this means that for all B in NP, we have a mapping reduction, a polynomial time mapping reduction from B to A. Okay, so A is NP complete if it's hard. So everything in NP is like has a mapping reduction to A. So A is harder than everything in NP in terms of polynomial time mapping reductions. And also A itself is an NP. Okay, so in particular, we must have this. But that's always true. So there's always a mapping reduction from a language to itself that you can just use the identity function. So this is always true. Okay, so all right, but if every language in NP is less than or equal to A, so it's has a mapping reduction to A, and A is in NP, then A is in some sense the hardest language in NP. But there could be ties, right? So if A is NP complete, then it kind of means A is in NP, but it's the hardest language in NP. But of course, there could be ties. So everything's up to polynomial factors anyway. So other languages might be tied with A for the claim of being the hardest language in NP. Okay. And we can also define P-space complete. Actually, we did define P-space complete. This definition already defines P-space complete. P-space is a class. So if you just put P-space instead of C here, then you would have the definition of P-space complete, and you can define completeness for every other class of languages. Okay. All right. So now the interesting claim is that there exist NP complete languages. So there is so the claim here is that there is there is an NP complete language. Okay, so let's prove it. So the proof is just take the language A, which asks you to decide if there's a witness that causes a verifier to accept. So for example, one way to do it would just be, okay, so we will give a, let's say the verifier V, some input to it. Let's give it like two numbers written in unary here. Okay, so it's this tuple. And then what we want to decide about this tuple is we want to decide whether there exists W in our alphabet. So we can pick the alphabet to be whatever we want, like 0, 1, let's say. If there exists W in alphabet of size at most K, such that V of XW accepts in less than or equal to L steps. Okay, so this will be the language A. So the language A asks, given a verifier and an input to it, and some budget for the witness size and budget for the time, decide whether there is a witness of that size that causes the verifier to accept within that time. Okay, that's the language A. So the A is a set of tuples. It's a language, so it's a set of tuples for which all of that holds. Okay, but deciding whether a tuple is an A really means deciding whether there's a witness that causes V to accept X within the budgets. Okay, so we can define A to be this, and then first of all, we claim that A is going to be in NP. Why is A in NP? That's one of the conditions we need to show for NP completeness, right? So why is A in NP? Well, because, we can find, for example, polynomial time verifier, right? What is a polynomial time verifier? So let's define this. The verifier will be, let's call this, V prime. So the verifier V prime, it will take in X and W. And then it will check, if X is formatted like, so X needs to be formatted like this. Maybe we should call it actually, let me call it a Y here. Let's just call the input Y instead of calling it X, so it's less confusing. So let's, so it needs to check that the input, the Y part of the input really has the right format. Okay, so so this is a format check. So format checks are generally efficient, like they're polynomial time things. So, and then if so, so V prime runs V of XW for L steps. Actually, we need to also check, that the size of W that we're given, this W, is at most K. Okay, where K is from here, it's part of the input Y. Okay. And then if so, the V runs, the V prime runs V of XW for L steps, and then accepts if it accepts. Okay, so first of all, because we're simulating something for only L steps, and L was part of our input size, right? The input size Y here contained, it was length at least L, right? Because the 0 to the L. Then this is and because V, sorry, so this causes V prime rather to run in polynomial time, because it only simulates a machine for L steps. Okay, and L was part of the input size. Okay, and then now if this tuple, if Y really is an A, then of course the witness W satisfying these conditions exists by definition of A. Okay, so and also the witness W will be of size at most K, and K is part of the input Y, so it's a witness of size polynomial in Y. Okay, so if Y is an A, then the witness W will exist that causes V prime to accept. On the other hand, if Y is not an A, then again, by definition, there won't be a witness W that causes all this to accept. Okay, so this shows that V prime is a valid polynomial time witness for A, and therefore A is an NP. Okay, so then the other question is, why is there a mapping reduction? So like, let's say B is an NP. We need to show that B polynomial time mapping reduces to A, right? So we need to show this. Okay, how do we show that? Let's say B is an NP. So what do we know? We know that there's a polynomial time verifier for B. So let's denote this V KLC, whatever, be a polytime verifier. Okay, so this is the verifier, and these are like the bounds on the runtime and size of the and witness size, right? So B is an NP. Okay, so given this, then we want to define a mapping reduction. We want this, right? We want a mapping reduction from B to A. Okay, and so what we'll do is given X, right? Then what we'll do is we will map X, like the function f, we will map X to this tuple, which is V comma X comma 0 to the K, or sorry, not 0 to the K rather, but 0 to the size of X to the K plus C, and then 0 to the size of X to the L plus C. Okay, so this is what the function f will do. And so first of all, note that this description of V doesn't depend on X. It's hard, it can be hard coded in. So if we're trying to compute f here, like if we're trying to define a machine M of f that computes f, then this description of V can be hard coded in. Okay, so that's like constant time to print. Then to write down X, so I mean M of X can always, we're mapping X to this tuple, so our input is basically X, so we can write down X here. That's not hard. Then we just need to compute the size of X to the K plus C and write down that many zeros, and the size of X to the L plus C. And that is polynomial time to write down polynomially many zeros. So that's polynomial time in the size of X. Okay, so this mapping function f can be computed in polynomial time. And then, you know, if X is in B, then, you know, then we claim that f of X is in A and vice versa. So we need to show this basically, right? So first, suppose X is in B, then that means that X is in B means that there exists W such that the size of W is at most X to the K plus C, and V of XW XX. Okay, but that by definition, then you know f of X is an A. That's just the definition of what it means for this tuple to be an A. Is exactly this. And actually, V of W accepts within X to the L plus C steps. Oops. Okay, so that's exactly what. So the polynomial time verifier condition of B exactly guarantees that f of X is an A. Okay. On the other hand, if X is not in B, suppose X was not in B, okay, then we know that there does not exist such W with exactly the same properties. But because there does not exist such W, then f of X will not be an A. Okay, because being an A for this tuple for f of X exactly asserts the conditions in the witness. Okay, so it's actually extremely straightforward from the definition of this language to show why this language is NP hard. So this language is both in NP, this language A is both in NP and is NP hard because every other language in NP immediately reduces to it. Okay, it's sort of from the verifier definition of NP, we've almost already shown that this one language is NP hard. And it's also, we just saw is an NP, so it's therefore NP complete. So there exists at least one NP complete language. Okay, so finally, there is this, this thing called the Cook-Levin theorem. Okay, which was actually independently shown by Cook and Levin, who were, the Levin was in the Soviet Union at the time. So they were not communicating with the West. Well, Levin was not communicating with the West, Cook was in the West. So it's sort of, some of this math was done independently. But the Cook-Levin theorem, you know, is a major theorem in the foundations of computer science in complexity theory. And it says not only is there an NP-complete language, which we've seen, but there's actually a natural NP-complete language. There's actually kind of a nice NP-complete language. And the nice NP-complete language is called 3-SAT. Okay, and to describe it, then, well, we'll first talk about SAT. SAT is the satisfiability problem. And the satisfiability problem is basically when you're you know, you imagine you have n bits, like which are called variable names, like x1, x2, up to xn. And these can take in values of 0 or 1, right? So these are Boolean. Each of them is Boolean. And in SAT, you're given basically this set of clauses, which are like, you know, x1 or this v means or x1 or x5. Okay, and then there's x2 or x3 or x7. Okay, and then you're given another clause, you know, x1 or not x2. I'll put a bar here for not. Okay, and then you know, not x2 or not x4, whatever. You're given some set of clauses. So each one of these things is called a clause. So there's some notation to know, like a thing like this, or even a negation. These guys are called literals. Literals. So a literal is a variable or a negated variable. I know I'm going to use this bar on top for negating a variable. Remember, these are all Boolean variables. They're 0 or 1. Okay, so negating it is like, well, 1 minus kind of thing. Okay, so these are all literals. Okay, and then an or of literals. So in just an or of some of them. One of these guys basically is called a clause. It's an or of some literals. So a clause is an or of literals. Okay, and the satisfiability instance is a set of these clauses. Okay, so it's a finite set of these clauses on some number of variables n. Okay, the number of variables can vary as well. So you can, any finite number of variables is allowed, basically. Okay, so SAT is basically the set of all descriptions of, you know, such a set S, such that S is a set of clauses which is satisfiable. Okay, so what do we mean by a set of clauses being satisfiable? We mean that there's a satisfying assignment, and an assignment to the variables of either 0 or 1 to each. Like, let's say x1 is 0, x2 is 1, xn is 1, whatever. So I want some sequence here of assignment to the variables, such that when I plug them in, every clause evaluates to true. So every clause, so remember, 0 or 1 evaluates to 1, right? And 1 or 1 evaluates to 1. But 0 or 0 evaluates to 0. I want everything to evaluate to 1. So I want everything to evaluate to true. Okay, so that's the satisfiability problem. I'm given a set of clauses and I want to satisfy all of them. If it's possible to satisfy all of them, then we include this set of clauses in the language SAT, in the language SAT. Okay, but if it's not possible, then it's not in the language SAT. So the language SAT is a set of all satisfiable sets of clauses. Okay, so That's SAT. 3SAT is the same thing, except the clauses each have to have size at most 3. So as I wrote here, the instance I wrote here is a 3SAT instance because every OR here is an OR of at most 3 literals. Okay, but in SAT, you can have ORs of more than 3 literals, but in 3SAT, they each have to have at most 3 literals. Okay. Okay, so that's the languages SAT and 3SAT. And the Cook-Levin theorem says, so the Cook-Levin theorem says that 3SAT is NP-complete. Okay, so first note that 3SAT, the set 3SAT, the language, is clearly in NP. Why? Because a witness can be the satisfying assignment, right? So if the input is an instance S, the witness can just be the satisfying assignment. Like the witness can just be like the 1 0 0, you know, 1 1 0 1, whatever. Like the satisfying assignment to the variables. And all you need to do is plug these in and check that each of the clauses evaluates true, like that they're all satisfied. So that's a pretty easy to do in polynomial time. Okay, so there is a polynomial time verifier that just needs such a witness, and then it will accept if this witness really is a satisfying assignment. And it's immediately clear that this polynomial time verifier is valid, like it really is a polynomial time verifier for 3SAT. So 3SAT is in NP, and also SAT is in NP. Yeah, they're similar languages. Okay, and then the real claim is that 3SAT or SAT, they're both also NP hard. Okay, and this is a bit harder to show. So the way to show that they're NP hard is actually, note that it actually suffices to show that A reduces to 3SAT. Why? Because we already, A is the language from earlier in the video. We already know that for all B and NP, B mapping reduces to A. We already know that, right? Because A was NP hard. But then we get B mapping reduces to A, and then A mapping reduces to 3SAT. And whoops, and then therefore we get that B will map reduce to 3SAT because this mapping reduction has this transitivity property. So to show that 3SAT is NP-complete, all we need to show, all we have left to show is that there's a mapping reduction from A to 3SAT. In other words, we can convert an A instance into a 3SAT instance, such that the instance is an A if 3SAT instance is satisfied. Okay, so in other words, what we want to do is we want to take an input which looks like this. I mean, checking the formatting is easy, so I'm going to assume that that's already done when we start. So checking the formatting is easy. So let's suppose the input is formatted like this, and we want to check if it's an A. We want to convert this via some mapping reduction to kind of a satisfiability instance, okay, such that this is in A if and only if this thing is in 3SAT. Okay, so we want this kind of conversion F. Okay, and so the notes kind of go over the details of this, but the idea is that we are just looking, when is an instance like this in A? It's an instance is in A if there's a witness W of size at most K, of size at most K, such that V accepts X and W within L steps. So what we can do is we can consider like the Turing machine V. I can write down the tape of it for a second. Okay, and here's a tape of it. And let's just write down the tape here. And then let's write the input X like over here in this segment. We will write down the input X on the tape. Okay, and then over here next to it, okay, we will leave, we will want to write down W, Okay, but we will kind of leave this as variables, right? So we will write down variables W1, W2, up to Wn. You and I know that these are variables, but like imagine a computation working on this. And remember, sorry, this is up to K, right? W is the size of most K. And then recall that V only takes L steps. So we only need to write down this tape of length L in each direction from the starting position. So if the starting position is here, V will take only L steps. So it can't really travel more than L in each direction. So like 2L plus 1 will cover it, and V will never leave this range of the tape. Okay, so this is sort of the starting position of V. And also V has kind of a starting, like it starts as Q0, and it has its you know, it has this transition diagram of its internal states, right? But we can write down this Turing machine, and we can write down every configuration that V will take from this initial configuration in terms of the unknown variables W1 through WK. So the second configuration, okay, will look something similar. So I mean, actually, I don't know what they look like, but we write the second. So this is configuration number 1, configuration number 2. Imagine writing down all these configurations up to configuration number L. Okay. And then what we want to do is we basically want to write down logical Boolean formulas like with ands and ors and nots and whatever, that enforce the condition that that this transcript follows from this one. Okay, and here we have internal states. So what we're going to need to do is we're going to need to translate that into also Boolean variables. So we will have a Boolean variable, like maybe a variable, you know, alpha Q0 that tells us whether or not we're in Q0. So alpha Q0 equals 1 at the beginning, telling us we're in the state Q0. We'll also have other Boolean variables like alpha Q1, which is set to false because we're not in Q1 at the beginning. So we're going to have these set of variables that represent which internal state we're in. Okay, and so in each of these L different configurations, we will have these sets of variables, alpha Q0 and alpha Q1, and so on. So we're going to have all these variables. So we're going to have variables. So at the beginning, we set all of this to, okay, so in each of these states, we'll have variables for every position of the tape. Okay, we'll also have a variable for whether the tape head is in that position. So maybe we will have for each position here, a variable T1, T2, T3, a Boolean variable, it's either 0 or 1, that tells you whether the head is there. So here T, whatever this is, TL will equal 1, but all the rest will equal 0. Okay, so we're going to have this bajillion variables, and we'll have these everywhere for each of these L configurations. And then what we're trying to do is we're trying to represent the entire computational logic of a Turing machine, of a generic Turing machine, in terms of these logical Boolean conditions that basically say that, for example, the tape head at position at time step I must be either to the left or right of time step I minus 1. Okay, and whether it's to the left or right must depend on the transition rule. So it depends on, you know, the variable that is at you know, at the position of the tape head, and also on the internal states. So we're going to have these logical rules that tell us that, you know, kind of like an if you are in position, you know, if you're in position, you know, 17 and are seeing 1 on the tape, okay, and you are in internal state Q3 at time step, at time step 5. Okay, then you are in position, let's say 18, and have, or actually, if you're seeing 1, okay, and let's keep going, and at position 18 there is a 0. Okay, so if all this happens, then you are now at step 6 you're in position 18 and have a 1 written at position 17, and are seeing 0, and are in internal state, Q7. Okay, so this just represents one single transition that you could take out of all possible transitions. One single transition you could take from step 5 to step 6. Okay, so it's telling you if you are currently in position T17, meaning that this indicator variable T17 happens to be 1. Okay, and you're seeing a 1 on the tape. This means like the tape position, like we need some variables for the tape positions. But if the tape position, I'm running out of variable names. If tape position beta, beta 17 is equal to 1 as well, because you're seeing a 1 there. Okay, and you're in internal state Q3, so alpha, alpha Q3 is equal to 1, and in position 18 there's a 0, right? So anyway, so you have these sets of variables, whatever, 18, 0. Anyway, something like this. You have these set of variables, and you basically and all of that is at step 5. So this is comma 5. Like all these variables are indexed by 5 as well. So if you have these set of variables with that assignment, then it implies that a different set of variables for step 6, a different set of variables have some other assignments. And so you have these rules, and it turns out there's only polynomially many such rules. In terms of the number of positions of this tape, which is like 2l plus 1 that you need to consider, and the number of configurations you need to consider, which is L. Okay, and then the number of internal states, and you're basically just polynomial in all of these. Number of total transitions rule like this, then you can write down that tell you where you must have gone given what you would have seen in the previous step. So you kind of write down all these rules, and each of these is a Boolean formula, usually of the form if then, but you can translate an if then into kind of ands and ors, as it turns out. So for example, an if then, for Boolean variables, A arrow B, A implies B, is the same as saying, either not A or B. Okay, so these are logically equivalent. So you can translate an if into an or, basically. Okay, and then so you'd have these ors of ands, and you can use De Morgan's rule to translate an or of ands into an and of ors. Okay, and you basically keep doing these transformation to transform this whole ugly logical statement that tells you how this computation will unfold correctly into a bunch of an and of a bunch of ors. And at the end, you want to make sure that the final state here, alpha, basically alpha q ac comma L as position L, you basically want that to be the accept state. So you want that to be a 1. Okay, so you want this to hold at the end. So you basically create this giant list of clauses, but it turns out to only be polynomial size in terms of L and K and X. So basically in terms of input size, it will be only polynomial size, and in terms of the internal states of V. Okay, and so you create this gigantic set of clauses, which you can translate into an and of ors, basically. And therefore just a set of clauses that all must be satisfied. So the and of ors just becomes a set of ors, all of which must be satisfied. So and that's your instant S, and that the S will be an input to sat, not to 3-sat. To get 3-sat, you also need to make sure that all the clauses are size most 3. And there's another conversion trick that's mentioned in the notes for how to reduce the size of clauses from arbitrary size down to 3. And that expands the number of clauses by a bunch as well. Okay, so, and then the point is that all of this can be done in polynomial time. Okay, so this, given such an instance, you can create this bizarre and gigantic set of clauses that basically asserts that once the computation of V runs on X and a set of variables W1 through WK, once this computation runs for L steps, it will reach an accept state. Okay, so now you have these variables there that are free variables that have not been, their values haven't been forced. Some of these other variables, their values will be forced, but these are free variables, and an assignment to them exists that satisfies this set of clauses if and only if a witness W exists that is accepted by V. So this is the end of this kind of long story of how you convert this language into the 3-sat inverse. Okay, the notes have a little bit more detail. The full detail is pretty complicated, so we won't see like the proof in all detail in this course. But this is sort of the gist of the argument. This W is basically you know, Boolean variables that together you know, the bits of W basically become variables here in your satisfiability instance. And you have some other variables that become forced to be equal. You force them to be equal to some function of your previous variables via your complicated set of clauses. Okay. So that's it. So that's the story of 3-sat. 3-sat is a fairly natural language which is NP-complete. And you can show other languages that are NP-complete. We can show a language, you know, let's say we want to show a language B is NP-complete. All we need to show is we need to show B is in NP, and we need to show that B, there's a mapping reduction from 3-sat to B. So that together will imply that B is NP-complete. And this has been done for a lot of languages. And once you've done this for another language B, you can use B to prove even more things are NP-complete. They kind of proliferate like this. Like if I want to show C is NP-complete, then I will show B mapping reduces to C, and then also that C is an NP. So I can these things proliferate. If I have a language, if I show a language B is NP-complete, I can show another language C is NP-complete more easily because now I can use B as the starting point for my reduction. And once I've done this, then I can also use C as a starting point for my reduction. So basically, it just gets easier and easier over time to show that languages are NP-complete, right? Because more and more NP-complete languages are known, and the more are known, the